welcome back. We're going to continue our discussion of charged particle interactions with matter, and I'm going to move on now. In the last video, we learned about radiative losses. So that's a process whereby a charged particle, let's say an electron, it comes by, let's say, the nucleus of the atom. It gets bent around by Coulomb interactions, and it releases a Bremsstrahlung photon. That's a radiative loss. That's one way that particle can lose energy. And now we're going to move on and study the other primary mechanism. Here we go. So that other type of energy loss is collisional losses. In other words, the electron that comes in interacting with electrons in the orbit of the atom. Now, before I dig into this too deeply, let me back up and motivate this a little bit more clinically. So collisional losses, that's the way that dose is deposited in tissue. Okay, the energy of the electron goes into the energy of the tissue, the atoms in the tissue. This other type of loss, radiative losses, that produces X-rays, and that's the way that we produce X-ray beams. An electron interacting and producing X-rays that we use either for diagnostic purposes or for therapy. And we're going to see much more of those practical applications in the next videos. Okay, but for now I'm going to jump back and talk about the collisional losses. So there's a couple of things to note here, factoids. So first of all, single collisions can actually sometimes impart a lot of energy if they're sort of a head-on billiard ball type collision. And this can actually be up to 50% of the energy. Second, this collisional stopping power, it's going to depend on the number of electrons per unit gram. That sort of makes sense because more electrons, more collisions. And so it decreases somewhat at higher Z. And that's a relatively small decrease. But you'll remember that as you go up in Z, you get more neutrons per atom. And so actually the number of electrons per unit gram goes down slightly as you go up in Z. So putting this all together then, here is the plot for these dependencies. And I want you to spend a few minutes staring at this and becoming familiar with it. First of all, you've already seen these two lines. These are the radiative stopping power losses, and remember again that it depends on Z and it increases with Z. Now these two curves up here are new ones, and these are the collisional losses that we just talked about. Okay, now you'll see here there's not very much energy dependence, and what happens is as you go up in Z, the collisional losses go down a little bit. That's that dependence on the number of electrons per unit gram. It's a relatively small change compared to this change in radiative losses, but there it is. And at some point these cross over. So far we've been talking about what happens with the electron when it interacts with matter, and I just want to spend a few minutes talking about the case for protons and how that's a little bit different. So the stopping power for protons is actually given by the beta Bloch formula, and I won't really go into it, but it's basically proportional to Z squared times, which is the atomic mass of the particle. So in the case of proton, it'd be 1 times big Z. That's the atomic mass of the absorbing medium, divided by the velocity squared of the particle, divided by the atomic mass of the medium, and then multiplied by this term called B, a term that describes the atomic stopping power. It depends on the speed and the ionization potential of the material. And so you got some interesting dependencies here. So first of all, it does not depend on mass for these heavy particles. unlike the other case we just saw. Number 2, it does depend on speed, and that's quite important, and you'll see that in a minute. Number 3, it does depend on atomic number. And number 4, it's much higher than for electrons. So here's what this looks like on these plots as a function of energy. This is for, now remember, this is for protons in this particular case. And in particular, what we're plotting here is protons in water. And you see the collisional stopping power is much higher than the radiative stopping power. Also, this is important, is that the collisional stopping power increases as the energy decreases. That's that 1 over v term in the stopping power, 1 over v squared term in the stopping power equation. And so you actually lose more energy as the particle slows down. We'll see that play out and so have some practical implications. All right, now let's move on to not just how much energy is lost by the particle, but how they actually travel in matter. Basically, I think here the important thing is just to have a qualitative understanding of how the different particles travel in matter. And so if you look at the case of an electron, it's a light particle and it doesn't really travel in straight lines as it goes through matter. It can actually take a tortuous path because it's small and it can be accelerated a lot by the nucleus and so on. And so that might be the path of the electron. That's it can undergo hard collisions in some cases, and that actually transfers a substantial amount of energy to the electron. And these are sometimes called delta rays. But a delta ray is just an electron that happens to be at high energy. Now for protons, it's quite different, and for heavy particles, it's quite different. Because they're not subject to so much acceleration as they travel through matter, you can think of it as kind of like the bowling ball versus the ping pong ball, and the proton just kind of can plow its way through. And it will undergo some Coulomb interactions, but they're relatively small deviations. And then with a heavy ion, it's even more extreme, and it just kind of travels in an even straighter line, is subject to even less acceleration. So in therapy, an important heavy ion might be a carbon atom, a carbon nucleus, and it goes really very much in a straightforward direction. All right, so that concludes the topic of charged particle interactions with matter. I'm going to leave you with a little further reading to study more. I encourage you to go back and really learn this deeply, because it's going to have all kinds of practical applications that we're going to see starting already in the next lectures. It's going to have impact on radiative penumbra in patients, inhomogeneity, let's say lung versus tissue. It's going to inform us about how photon beams are made in a LINAC or in an X-ray tube, and many, many other things. So all these fundamentals underlie all of what you're going to learn later. So I hope you take the time and understand this deeply, and then the rest of the lectures will be easier to understand. I'm going to do one more thing before I move on to the applications, which is I'm going to talk in the next video about the interactions of neutrons in matter, because that's going to be important for some applications as well. Thank you.